new sampling technology where you collect several increments and then you sort of compose and process at the lab to get a more representative soil result, especially in terms of risk evaluation. Anyway, each pile, we collected one soil made of 30 increments, and each increment location, we collected several aliquots of soil at different depths, because each pile was about 2-3 feet high and 100 foot long. So I think we had a pretty good distribution. Our sample was representing pretty good what the actual soil concentrations were. Samples were analyzed for naphthalene, GRO, and DRO, our contaminants of concern, and the GRO increments were not composed or composited. Composited is not really the right word, but they were not composed together into one container on site because we were concerned about volatilization. Usually what you do, you put all the increments in one jar with methanol, and then once at the lab you extract. But with methanol there's some concern about shipping, so we decided to put each increment, each little aliquot of soil into a single 40 ml vial. We froze all the vials for that soil we put all the vials for that sample, for each sample into a Ziploc bag, put it in the cooler. We froze all the samples, ship it to the lab, which was not Washington State University, this time was a commercial lab in California, and which is NELAP certified. And then there, under controlled conditions, they composited the sample and analyzed it. They processed it and analyzed it. This is a photo of our stockpiling area, several rows of soil and covered with 6 mil polyethylene. Results, so concentrations of naphthalene were between 0.17 and 13 milligrams per kilograms below the industrial action level of 40 milligrams per kilograms, and also below the residential 15. GRO, gasoline range organics, were between 150 and 1200 milligrams per kilograms below the industrial 3400, and mostly below the residential action level. DRO, same, below industrial and mostly below the residential. Like I said, all of the piles were below the industrial, and most of them, at least 85% of them, were below residential RAG-Gs. And I say at least because, like I said before, we remixed 15 piles, but only 4 were reanalyzed. The other were already meeting the industrial RAG-Gs, so we didn't really have to reanalyze and spend more money because we were working on a budget, so we couldn't just waste money. And we estimated that we achieved between 80 and 85% reduction. All excavated soil was reused on site as backfill, so no soil at all during the project was disposed at the local landfill, and that was a big achievement. And the time to implement the ESCO part, the excavation, treatment, backfilling, restoration, was about 6 months from mobilization to demobilization. We had some delays due to weather and some incidents on site, not health and safety related, but overall 6 months. This is a snapshot of the results. Basically, green means that the soil that was put back in these areas is below the residential action level. Yellow means above residential but below commercial industrial. And pile and area 6, soil from area 6, 8, and 14 were very close to the residential action levels, and they were remixed, and we didn't analyze them after the remixing, so probably they're also meeting the residential action level. So it was pretty good results. A little bit about cost. Overall, for subcontracting cost, including excavation, mixing, and everything, and also chemical procurement, we spent $750,000. $710,000, which means $225 per cubic yard of petroleum contaminated soil and $155 per cubic yard of treated treated soil. Because like I said before, we've retreated some of the soil, so the cost per treated cubic yard was a little lower. And overall, we saved $265,000 of government dollars, so 25% less than what was planned, which was, I think, pretty good because we did something sustainable, no soil to the landfill, saved money, and supported local economy. So it was pretty. This part of the project was pretty successful. Important for the success of this part of the project, for the ESCO part, was having a flexible plan, having both the client and the regulators on board, and very open to changes. They were really part of the team. We worked together, and we took every decision together. Having a flexible remediation plan was a must because otherwise, theoretically, you have a decision document right after the investigation, and what you do, you just take whatever the decision document says and you implement it. And if we did that, we would have done ISCO over the entire site using calcium peroxide, and based on bench test results, calcium peroxide wouldn't have worked. So probably we would have achieved nothing. And this is not to point fingers to anybody, it's just that when you do a feasibility study not based on actual lab data, you just use literature review and you don't have the actual site data, and sometimes it might not work, and this one would have been one of the cases. Lessons learned, ESCO is definitely a good, cost-effective and sustainable alternative to ISCO for source area remediation, especially if the area is not too large and the TOD, like I said before, is not too high. It is true that with ESCO we did not destroy completely the contamination, but the residual level in soil are below the acceptable level. There is no risk basically to the current receptors, which is basically base, the workers on site, on base. We also learned that pH is very high, is very site specific. We used a recommended dose, but like I said, we couldn't raise pH higher than 10. We ended up using twice as much dosage, and at that point we were successful. And so pH, PID, and persulfate residual monitoring during the mixing, during the oxidation reaction is very important. We also learned that the reaction doesn't generate too much heat, which in a way is good because it would create some safety concern, but on the other hand, sometimes it's not good because heat helps to decompose the persulfate, to activate the persulfate and destroy the contamination. And the reaction again was very fast. Then this is not critical, but water is important, and during reaction, the soil stayed pretty wet, probably also because we covered it for odor concerns, and we didn't have to use water after that. Right after ESCO, we conducted sampling, and we collected soil gas samples within and outside of the source area, so within the diamond-shaped red area, and also outside, but inside the blue line. And then we conducted subsurface soil multi-incremental sampling outside of the source area. Results show that the soil gas residual concentrations within the treatment area, the source area, were below the WRRCs for methane, but we had still some residual soil gas in the source area. Outside, where we didn't do anything other than treating the source zone, which usually helps, the soil was below the industrial WRRCs, but soil gas was above in most of the locations. So the final result was that source area, soil gas, soil was below, soil gas was, we had still some residual concentrations. Outside of the source, soil was below, soil gas above. So what we remain with is groundwater and soil, no action. They're both below the industrial action level, and we don't need to do anything else anymore. However, we still have some residual concentrations in soil gas, and that's why we did ISCO, and now we're conducting in situ, we're conducting long-term monitoring. So after that, we conducted ISCO to try and address residual concentrations in soil outside of the source to see if that helped to also address the soil gas. We conducted some what we call injectability test. It's sort of a pilot test on site to estimate the hydraulic parameters of our injections in terms of, for example, radius of influence, pressure, and things like that. And also evaluate if vertical injection will work better than horizontal injection. And we found out that horizontal injection were much more effective. You know, they had a larger area of influence. You know, the oxygen would spread out more easily than vertical. So we injected iron EDTA activated persulfate to target the most contaminated area, which was across the capillary fringe, right above and below the water table, basically. And we conducted 2 back-to-back injections, 2 weeks each over 1 month, because this phase of the project, we couldn't use a local, it's not that we couldn't, but we trusted, we decided to use a mainland subcontractors for the injection, because that's what they do for living, local subs. They have some experience, but not extensive experience. So we wanted to maximize the time of the mainland subcontractor on site, so we conducted 2 back-to-back injections with only 1 mobilization. We installed 20 horizontal wells and 22 verticals. Vertical because we had some space constraints, and we needed to address areas where we had high traffic, and excavating trenches was a problem. And we injected 176,000 gallons of iron EDTA activated sodium persulfate. This is a figure of our setup. These are horizontal wells, the lines, and the dots are vertical wells. So they're all outside of the source area. And we got pretty good coverage. We had little areas where, because of the asphalt, traffic, we couldn't probably reach 100% coverage, but overall we think it was 80-90% coverage. It was pretty good. And the radius of influence was probably even higher, so we probably reached close to higher than expected, so we probably covered close to 100% of the area. During injection, we monitored persulfate and iron to see how far the persulfate was going and if it was properly activated. And we also monitored the geochemical parameters. Basically, we noticed that wherever we would inject persulfate, with, like I said before, it decomposes and creates hydroxyl. Basically, it also generates oxygen, and that we saw that pretty much everywhere we injected persulfate, the oxidation reduction potential (ORP) was going super high. Oxygen was going super high. So basically, we were not only destroying contamination, but we were changing from anaerobic environment to aerobic, which is very favorable for bioremediation of petroleum contamination. The radius of influence we estimated based on these parameters was up to 15-20 feet in the unpaved area for the horizontal injection wells. And now we are in the post-injection monitoring phase, and we're basically monitoring soil gas quarterly. We also did some limited groundwater monitoring right after the injection, because we wanted to see if we had residual persulfate a month and a half after the injection. We found out that we did have pretty high residual persulfate next to the injection wells, but at the boundary of the radius of the area of influence, it was very low or none. But we know from pilot test study, bench test study, and literature that persulfate can stick around for quite a bit, probably up to a year, which is good. So you have slow, constant treatment of the soil. And usually pH, if you use lime, readjust pretty quick, but in this case we used, for the injection, because we also had that concern, we used iron EDTA, which has an equal pH, so the microbial population would not be affected, and bioremediation is still ongoing, which is helping big time. That's pretty much it. Like I said, we're still working. The first phase of the project was very successful. The second one, preliminary results don't look as good, but we're still hopeful. We, like I said, we achieved good destruction for the source area, and we met the objective. And we implemented a sustainable solution, which was a big achievement for us. And the client is very, very happy. And hopefully also with time, I think the site will re-equilibrate. We still have residual persulfate, and with time monitor. If we're not gonna remediate the soil gas as well, for sure what we did outside of the source area will help to at least reduce the remediation time and monitor natural attenuation. The biodegradation, natural degradation will take care of it, but it might take a bit. So any questions, happy to answer.
How long after the original spill was your remediation action conducted?
Yeah, it was actually a pretty long time. It was the spill was in 1997, and we started in 2012. So there was already some biodegradation going on, and we saw that.
It's surprising that the contamination was still there after such a long time.
Yeah, well, yes and no. I mean, concentrations were really high, and I've seen sites where, with modeling or even experience, of course I haven't lived long enough to see that, but I've seen sites that after 15, 20 years, they're still, with high concentrations, and modeling will tell you that other sites that I've worked on, the concentrations will stick around for 100 years. So it's not really cost effective to do any remediation, and sometimes it's actually technically it's not doable to reduce concentrations below the actual level.
I was curious why you settled on the chemical oxidation route rather than trying to enhance bioremediation or do some sparging and that sort of thing.
Yeah, we thought about it doing. We were first of all we were working on a decision document, which like I said, we deviated from it, but we not significantly. I mean, we implemented the remedial alternative that was in the decision document with some deviations like ESCO, of course, but the technology was pretty much the same. Instead of in situ, we did ex situ, and we changed the chemical. Air sparging, for example, you mentioned air sparging, it would have worked probably very good if we had a major concern with groundwater. However, groundwater was actually below the industrial RAGGs. We had some residual concentrations in groundwater, of course. It's not pristine, but concentrations were not high, and we didn't have to do anything to make the remedial action cleanup goals because we were already meeting. We also looked at other technologies, like for example, ozone for the beta zone, because soil gas was definitely a concern. However, we think that the problem, even if we see soil gas residual concentration, my gut feel, and again, this was not a research project. We were working on budget, schedule, and what we were told to do. But my gut feel is that the major problem is I want to say more contamination than we thought in soil, even below the water table. So when we started injecting at the very first, we saw some actually increase in concentrations. That means that we were probably attacking the soil contamination stick to the soil, even below the water table, but there was more than we thought. So we were desorbing, destroying, but there was more than we thought, so the injected oxygen was not enough to destroy the whole contamination. And that's typical, because you don't remediate. I've never seen a site remediated with one injection. Usually you have 2, 3, multiple injections. But anyway, we think that ISCO or ESCO, we know that ESCO was probably a very good technology for the soil. Probably not ideal for soil gas, but I think if we address soil, eventually we will address soil gas as well. But definitely there are other technologies that are normally used, like sparging, venting, there are many.
How much soil did you take out? What depth?
We went down to, originally we thought we would need to go down to 6 feet, but we ended up going to 8 feet. Because like I said, yeah, it was a lot. And there was more than we thought, and we saw it in the source area, and I'm sure that outside of the source area where we don't know exactly, because the investigation done in 2010 was pretty large, but it's never 100% complete. You never have what you actually need. Otherwise you end up spending a lot of money. You had a question?
Yeah, how deep was the uncontaminated layer at the top?
That was about 3.5 feet. So
Okay, and then you had about 5 feet of contaminated.
Yeah,
layer.
more or
Now,
less.
When you excavated, did you separate the?
Yeah, what we did, we first, over the entire source area, we excavated the first 3 feet, 2 or 3 feet of overburden, and we stockpiled it separately.
Okay.
We knew that was clean based on remedial investigation results, based on PID screening, the photoionization detector. We saw the volatile compounds were very low or non-detected. So we stockpiled separately. Once we started seeing contamination, visual observation and instrumental, that's when we said, okay, we're good, start treating, and that was our treatment area, between 3 and 8 approximately.
And then when you put it back, you
Put it back, we did the same on
The
the other,
same.
yeah, we
Okay.
put the treated soil first
Yeah.
at the bottom,
Yeah, yeah.
and then the clean top, the clean at the top. Yeah.
How deep is the water table?
It's about 4 feet and it's tidally influenced. Yeah. 4.5 or something like that.
400.
Yeah, 4.5.
And you don't think there was contamination because it's been a long time since?
No, we know that there was some contamination in groundwater. We know that, but the concentrations were not high enough to cause a concern. There was no risk. So concentrations were below the industrial action level, so there is no risk to the current receptors. And once we did the injection, we know that we treated groundwater as well. So the expectation is that, and that's why the regulator didn't ask us to do any monitoring for groundwater, because once we injected persulfate, we know that we also treated groundwater. That didn't need any treatment, but we probably did some good also for groundwater.
But you don't think that between the accident and the start of remediation, something happened, like could have migrated outside the area?
No, I wouldn't have that concern because, persulfate, by injecting, we, like I said before, we destroy some contamination. We also desorb, but we also, whatever was desorbed was probably destroyed. And then in the long term, there is residual persulfate and it generates oxygen, which enhance bioremediation. So I don't see how we could do worse, basically, for groundwater.
Before the treatment, you don't think it could have migrated?
Well, we started treatment a few months after the actual data. So in a few months, I don't think there would be. We had data from 2010, 2011 that showed that concentrations in groundwater were below the action level.
But you don't think that perhaps what with the ambient groundwater flow towards the ocean, a plume could have migrated oceanward somewhere? Did you
Well,
ever
you know,
try sampling along?
we have data over 10 years span that didn't show any concern. And actually we, as a separate project, we did remediation and monitoring also a site that is immediately downgrading of our site. And by the way, like I said, groundwater it is flowing, theoretically it is flowing towards the ocean, but between tidal influence and between the water table being almost flat, I don't think the water migrates very far anyway. Because tidal fluctuation helps to oxygenate the water table, and at the same time the net effect is that the water doesn't move very far, and especially not very fast. So that wasn't a big concern. We had recent data, and we also had data downgrading that showed that groundwater was not a concern.
You remixed 4 or 5 of the stockpiles that were above the residential, but below the industrial limits. Is that correct?
We actually remixed. We remixed the 4 initial stockpiles where we could not achieve high enough pH, and for those we had DRO that were actually above the industrial because we could not achieve pH, we could not activate the persulfate. And together with those, we treated another 11 piles, we retreated another 11 piles, but those were already meeting the industrial RAGGs. We retreated them anyway because, after first mix, we saw the concentrations were not, were below the action levels, but we're still, we still had some residual, relatively high concentration, so we added some oxygen, and based on the concentrations we saw in the lab, we added full dosage or half dosage or quarter dosage we wanted to finish basically all the persulfate and make the most out of what we had, and so we're pretty sure that those piles, those 11 piles, were already meeting the industrial, and they were very close to residential. After remixing, probably, most likely, they also went below residential.
Okay. So the 4 that were exceeding industrial were then reanalyzed after remixing?
Yeah, and after remixing we saw some interesting results. And we met, for 2 of them we met both industrial and residential. For the other 2 we met industrial, but we were slightly above residential. And the interesting part is that DRO decreased about 70 or 80%. But GRO concentrations actually remain constant, and in one case or 2, we saw a slight increase. Basically, the persulfate wasn't activated properly, but it's still strong oxygen. Plus, when you mix the soil, you have some volatilization. So basically, we took care of the GRO during the first mix. The second mix helped to address the DRO as well. And another explanation could be that, during the second mix, we didn't do, again, it was not a research project, but what could have happened, and I don't have data to confirm, but what could have happened is that during the second mix, concentrations of DRO were very high, and by mixing with oxygen, the higher chain hydrocarbons basically broke down into lower chain hydrocarbons, and that's why the net effect was the GRO maybe slightly increased, but it wasn't real GRO, it was degradation, destruction of DRO. But that's speculation, I don't know. That's a possibility.
And then you were saying that you, for the VOCs, sampled your increments into 40 mil vials and shipped those to the lab. So I'm assuming that you're using a 5 gram increment.
Yes.
So there's going to be significant headspace in that bowl.
Yeah, like I said, we froze them right away while we were collecting. They went into a cooler with dry ice, shipped to the lab all together. And at the lab, inside a cooler refrigerator room, under controlled condition, when they were still frozen, they were put in a jar with methanol and extracted.
Okay. Do you know how long that took before they were able to actually do that compositing or extraction?
Right away. When it gets to the lab, they do it right away. And then and the actual sampling, analysis process is like any other VOC. You know, for the volatile portion, the processing of the multi-incremental samples is not the same as the non-volatile, where you sieve, dry. For the volatile part, you just analyze. The multi-incremental part is the collection part, but the processing is the same as any other.
Yeah,
volatile.
you just inject that methanol into the
Yeah.
effectively.
Yeah.
Yeah.
Good. So, thank you very much.